Let us welcome Dr. Muhammad Reza.
Thank you very much, Ms. Nur Hassana. Good morning, everyone. So today, I'm very honored to get this invitation to give a keynote speech in MechCon 2022. So I will start by sharing my screen. Hope everyone can see my screen. Yes?
Yes, Doctor. Yes,
Okay.
we can see.
Yeah.
Yeah.
Thank you. So today my presentation will be on renewable energy integration to power system for a sustainable future. It has been explained by Ms. Nur Hassana about my background. So basically, I'm originally from Bandung, Indonesia, and I spent my childhood schools until bachelor's in Bandung before moving to the Netherlands and spent almost 8 years there to finish a master and PhDs and moved to Sweden and stayed there for around 10 years before decided to coming back to Indonesia like 6 years ago, where since 2011 I've been teaching at Telkom University that's a good collaboration with Multimedia University in Malaysia, and since last year I am a full-time PLN engineering director, but I'm still teaching actually, so on a weekly basis. And with this online, it's also even more easy to keep teaching at university because I believe it's not only good to share knowledge with academia, but also actually to learn theory and see how it's applied in a practical world. So the outline of my presentation will start from sustainability in the future of electrical power systems, why we are actually in these situations, that we have to basically provide more sustainability for our electrical power system in the future. Then I will talk a little bit on the fundamental operation of power systems. Uh, Maybe some of you are familiar with power systems or power engineering in general, but I would like to talk about the fundamental issues because this will be the basis for the discussion or the presentation today, where I will continue with the characteristics of renewable energy sources and the challenges of the integration of these renewable energy sources to power systems after we understand the fundamental operation of the power systems. And I will conclude my presentation today with the mitigations of how we can uh, anticipate and overcome the challenges given by the integration of renewable energy sources to the power systems. So when we are talking about sustainability in the future of electrical power systems, we started from this global, let's say, intention to reduce the global greenhouse gas emissions. And if we see, this is from 2016, but quoted in 2022, uh, World Resources Institute, that the global greenhouse gas emission by sector, we see that the energy sector contributes almost three-quarters of all greenhouse gas emission globally, from which half of these energy sectors is from electricity sector. So it's fair to say that working in the electricity sectors, actually, if we can contribute of reducing the global greenhouse gas emissions in the sectors, it will contribute significantly to the reduction of global greenhouse gas emission globally. And that brings energy world in this energy dilemma in which that we have to provide energy, including electricity, that is secure, uh, environmental friendly, and uh, the energy equity is accessible and affordable for everyone to use. So we have to deliver energy, or in this context, electrical energy that is always available, that is reliable, resilience to any disturbances, and stable when there is some disturbances in the system. And energy equity means that it must be accessible, affordable for domestic and commercial use, and last but not least, environmentally friendly and environmentally sustainably. That is, it will not give a potential environmental harm and climate change impacts, meaning that we have to deliver the energy efficiently, and we have to consider decarbonization, and we have to keep the air quality high. So this is the dilemma because it's not easy to achieve three of these aspects when we have to deliver energy or electrical energy to the customers. So I will try to explain as the basic fundamental operation of power systems, starting from the overall system is electrical power system is actually consists of in the beginning the electric generation system that generates electricity from different sources, converting different energy, kinetic energy, potential energy, chemical energy into electricity that will be transmitted over transmission lines and several stations before it comes to the distribution station and it's distributed to different type of loads from commercial, industrial, and residential customers. So it works by the basic fundamental operations that in electrical power system, electricity generation must match the demand precisely at any instant on a second by second basis because it's not practical to say to store electrical energy in a large scale. Yes, we are uh, storing electrical energy in power bank, batteries, and so forth, but it's not practical to store like the energy used for the whole country in an energy storage system. It's just not practical yet, technically. So whatever we consume in one electrical power system at the load side, we have to actually generate exactly the same amount of energy at the generation side, trans- transmitted via transmission and distribution system. So meaning that we have to generate uh, the load and the losses that occurs in the systems. So in the classical power system operations, we are having this electrical frequency in Indonesia and I think most of Asian countries it's 50 hertz as indicators. So it means that this electrical system that is working based on an alternating current works at a certain frequency, 50 hertz for example, and that frequency must remain constant at all times. And that is actually an indicator that the generation at the load is balanced in the system at all times. So in the middle is the case when the generation equals the load, the frequency remains at 50 hertz. When the load is more than the generation, like in the left side graphic there, that the frequency will goes down less than 50 hertz. And if the generation is more than the load, the frequency will go higher than 50 hertz. And the problem is, quote unquote, the problem is electricity load varies with time. We understand that at home, we actually almost impossible to keep a load constant at all time when we actually operate different electrical appliances according to our needs. So this is, for example, a load profile in a household that usually will peak around 7 in the morning and again around 7 in the evening because that is when the people in the residential will have activities. making coffee or watching television and so forth. So electricity load varies with time. And load is not only residential, if you see again in this illustration, it has also commercial, it has also industrial customers that also have a different characteristic or profile of load demand. So industries, for example, may tend to have a constant load 24 hours, even 24/7, 24 hours, 7 days. Commercials will peak around noon. It is like offices, for example, schools, or it may peak a little bit shifted to the evening if it's like malls, etc. And residential may have peaks in the morning and the evening. Overall, basically, electricity is not like an always constant power consumption in the system. And power network operator task is actually to maintain the system frequency at 50 Hz or 60 Hz with a very small deviation margin that is regulated within the national utility grid code. So you can see in the figure here that 50.004, that is actually the frequency. I mean, ideally we are target 50.000 hertz, but it may work in a small deviation, but that is actually the main task of power or utility network operators to keep the frequency at a very small deviation from the 50 hertz frequency value. So fundamentally, power system operation is balancing the electricity generation with the load. So at the left side figure, you can see an illustration of how load fluctuates in 24 hours daily. And in the right-hand figure, you can see that actually the power system operators will operate different power systems, power generation in the system that is controlled to match the supply. So how they do it? Basically, uh, they do it by having some generation with both base generators, the gray there, and the orange one, the pickers, that can flexibly follow the load. It may happen, let's say, in the in the slow or steady state situations like 24 hours a day, or it may also happen during a very short time, during seconds or minutes, when there is some disturbance in the system. So, for example, in the figures you will see, when there is a disturbance in the system, like the load is less than the generation, the frequency will go higher than 50 hertz, and basically the operators must control the generators to reduce the power generation or to adjust so the frequency can achieve again the stable 50 hertz value. And the same when the generation is less than the load, the frequency goes down. Again, the operator must control the generators so then the frequency goes back to 50 hertz. How they do it is by if we are actually operating a classical fossil fuel based generators, quote unquote, it is easy to control the generation output. We can see number one, we know that load varies, load fluctuates, and we can control the fuel in such that the fuels can be injected to the generation system, so then the output power for the generators will match the daily or the load profile. And this has happened for many decades in the operation of power system. So now comes the renewable energy sources. For low carbon transition renewable energy sources, the most popular ones are hydropower because it is uh, kind of flexibly for small, medium to large scale power generation, geothermal, solar, and wind. But hydropower and geothermal especially has some drawbacks in terms of a project planning and project execution can take quite long time, can take years from the planning, from the survey, planning, and implement construction and implementation until its operation. So today, more and more wind and solar powers are becoming more and more popular because the technology makes the cost is becoming more and more competitive. Sources are available practically in many countries and it's flexible for small to large scale of implementation. It's modular. The cons is also actually mentioned in the session before by Professor Lee, is that it's intermittent and it's non-dispatchable. It cannot be controlled because it depends on the nature of the source itself. They cannot be controlled by the human. So if you see solar photovoltaic, it generates electricity by turning photons into electron flows, which is in a closed circuit. It will, uh, you know, uh, yeah, basically generate electricity in that circuit. And you can see in the right-hand side that the PV output power is actually linear to the solar intensity. And we know from the measurement that the solar intensity is not always constant. It is basically a function of the sunlight that is kind of, a peaking in the at noon and then reducing towards the evening. And also it's actually quite affected by clouds, for example, moving that cover the photovoltaic. So then the solar intensity and the output power is not constant and it's kind of intermittent in a way. Wind power is similar in a way that basically in wind power we are converting a kinetic energy from the wind to electricity and it means we have to convert the mass and the speed. We have this density times volume and we have the volume as the area of the blade times the velocity of the wind and the length of the time for unit of air to pass through the loop. And this actually will show that eventually the wind power output is a function of the cube of the wind velocity. So again, it's not linear and the wind measurement is also quite, stochastically fluctuates along time. So likewise, the output power of the wind turbine can be expected also will fluctuate accordingly to the wind velocity in the input of the wind turbine. So that brings challenges of renewable energy integration to power systems. When we take, for example, solar photovoltaic, we know that it peaks during noontime, there is not generating power during evening, and it may also have some cloudy day, if it has some spikes and some dip in the power output. Basically cannot be dispatched and quote unquote independent to the load. So when you are having like a daily load set and you have PV power generation, you will have some area where the load is not covered by the PV power generation, and on the other hand, there is case that the PV power generation is generating power and no load. So how we handle this? Because again, power system operation fundamentally, we must always balance the generation and the load. In the wind, it's the same. If you see, it fluctuates during the generation, during the day, and the load has its own profile. So, in the short term, when we have a case that the load is then less than the generation because we have more, for example, PV power generation, or we have like high wind, and the load is still remain the same, what can we do to keep the frequency remain 50, still 50 hertz? Because we cannot control the fuel to the generator. We cannot control the input of the energy source to the generator. And we said when we have more load and we have like a constant at an instant time power generation from the photovoltaic and from the wind. The frequency goes below 60 hertz. What can we do? Because we do not have kind of flexibility or controllability like when we are having a classical power system or classical power generation. So that brings the challenges to the operation of power system. So now, what kind of mitigation that we can do to mitigate these challenges to power systems? There are many techniques. The one of these techniques, which is very technical, which is so-called flexible power system. We remember that the power system consists of generation, transmission, and distribution and the load. So basically, flexible power system is preparing power system to have flexibility that at each of these subsystems, we actually can control that the system will be flexible enough or smart enough to anticipate or to compensate the intermittency of renewable energy sources. So, for example, at the generation side, what we can do, we actually can have a quick responding power plant, for example, of gas or hydropower basis, that is tuned in a way that it can ramp up and run down quick enough, quickly enough, so when the renewable energy fluctuates, we can control the compensating output from the gas or hydropower plant to match at all times the load or the demand required in the system. And how to do it? That requires a certain generator technology, a system control technology, fine tuning, parameter tuning, etc. But that must be done if we want to keep the system stable at all times. And then another way is actually to introduce renewable energy forecasting. Yes, we have some stochastic behavior with solar PV power generation, wind turbine, but actually we may have also some technology or forecasting technology that can be integrated in our PV farm or wind farm that can, to some extent, bring the margin of the fluctuation quite more, or at least it can be estimated quite accurately. We may uh, combine this with different methods, with satellite measurement methods, database, and artificial intelligence. But basically, the idea is to have more as accurate as possible of output power forecast of the renewable energy uh, generation. And then we can also have like renewable energy with the controlled inertia or controlled curtailment, meaning that we may oversize our wind turbine, we may oversize our PV system, but we keep some margin that we do not connect all power output to the system. So we have like some flexibility to some extent to reconnect some PV system or PV panels, or we can adjust some, for example, the pitch angle of the wind turbine so we can generate power for some time, and then we can have some flexibility to match the demand when it will require. The second one is we may have energy storage system or battery energy storage system where we can store some of the energy in mechanical form like in batteries and the palm hado system storage or in thermal storage so that when we generate power from the renewable energy generation, we can store this energy and we can use this energy later on. It can be used in two types. It can be used to let's say as load shifting or generation shifting to provide energy in the evening, for example, when there is no power output from the TV, or to smooth the output from the renewable energy sources of PV or wind turbine type, so that it's smooth enough that it will not cause any unnecessary disturbance or reduce the quality of supply in the system. The third one is a smart grid, meaning that we can have transmission and distribution system extensions in such that the transmission and distribution system actually involves that we have flexibility to connect renewable energy generation to the loads. And we may also have like an advanced network management, a smart grid system to basically control the flow, to balance the load and the generation at all times. And last but not least, we can also manage or control the load, the, the distribution side, the demand side management at industrial, commercial, and residential customers by, in a smart way, we match the load with the generation. For example, we control that the load, which is quote unquote independent in time, to operate when there is power generation uh, from our renewable energy system, renewable energy generation system. So this is an illustration to be more detailed. For fast response generation, for example, in this case, we use hydropower. So when we are having a daily load profile fluctuates along the day, we may have hydropower unit that have a reservoir, that have water storage in the dam that can be controlled by a flow control through the control gate to, for example, to flow more, meaning to uh, to generate more electricity by converting the hydro kinetic energy from the hydro to electric energy using the turbine and the generators, and then it will go it will go with to the power grid and to match the delivery provide. So in this case, the fast response can compensate whatever renewable energy sources that is originally used to supply the daily loads, and the hydropower can match the, the difference between the daily load profile and the renewable energy power generation. The second one is renewable energy generation forecast. Uh, it may be a combination of different techniques. I mean, it can be using like satellite data or database data, or it can be a combined with real measurements at each of these wind turbine and wind farms, combined with the database and satellite data and some artificial intelligence techniques. So the goal here is actually to provide as accurate as possible forecast to the utility, so then the utility operator can consider this as a quote unquote almost a dispatchable power plant, so it's easier for them to operate the system as a whole. Or we actually can have a battery energy storage to store the surplus energy from the PV system during the day, and then we use during night time. So basically, in this case, the battery energy storage system will store the energy during the day and shift the generation to the night time. Grid extension, it can be done nationally, meaning have like loads connected by interconnections in transmission and distribution system. We have more flexibility to put the PV system or wind turbine system, for example, in the location where the solar radiations or the wind speeds are the most optimal, and then we can supply the power to different loads more flexibly because the loads are interconnected. And it can also be done in the regional level between countries, like has been discussed many years ago for Europe and North Africa, and also recently in Asia, particularly Asia Pacific, that interconnect reaching different countries may also bring flexibility to supply more and more renewable energy to different loads in different countries, in different demand countries. Uh, Last not least is the demand side management in terms of smart home. That is by having more and more equipment at home that is working on electricity basis, including, for example, cooking system, air conditioner fluid, or even electricity vehicles, but also by having some possible power generators at home that controlled by inverters, smart meters, and controllers that we can actually, to some extent, control the demand and the generation at home, at our home, that it will interact with the utility in a smarter way, that it will not bring, let's say, unnecessarily uh, fluctuating power to the system, meaning the operator will be more easily to control the system and bring system to stability at all times. It can be done also in smart and city level, at smart city level, by having the same ideas but controlling instead of one house to control the whole city. So to conclude, renewable energy integration is required for sustainable future in power system because of the requirement to reduce the global greenhouse gas, you know, emission globally. But renewable energy, especially wind and solar, which is among the most popular, has some characteristics that may be kind of bring some risk to the system, such as intermittency. So we have to consider this and we have to bring the integration to the system by mitigating the fluctuation problem. So the flow will be like there will be electricity demand growth, and we should opt for low carbon transition, meaning green renewables. Solar and wind are the most among the most popular, but we have some intermittency. So we have to keep in mind that system must always be in the balance at all times, both availability and stability, and we may need to improve the flexible power system, and there are many technology alternatives that one alternative could be working best in some situation or some anecdotes, and some other alternatives may be working better in other alternatives and other places. So this is some my presentation, and thank you. So please, if there is any question.